All right, I think it's rocking and rolling now.
So what do we really know about this problem? Let's try to get to some things that might help us out. We know that the frequency equals 10 hertz. Another way of writing hertz, right? By default, we know the periodicity of this equals 1/10. What else do we really know? I think we know the amplitude of this motion would be 0.03 meters. So those are like the first three really easy things we can pick out of this, right? We know that T also equals 2 pi over angular frequency. So why don't we solve for an angular frequency too? Let's come up with a number for this and see if it can help us out. Go ahead and take that 0.1. I think I got a number I like. We get 62.8 radians per second. Sound good? So I think that's what you get when you take 6.28 divided by 0.1, you get 62.8. So that makes sense to me. So now it says calculate the acceleration of the floor due to the simple harmonic motion. Well, here's what I know right now. I know the simple harmonic motion deals with centripetal acceleration. Equals v squared over r. I also know that linear acceleration equals r times alpha. So we've got a couple things we can put together as far as this problem. They didn't give us an accelerant. They didn't give us a radius of this. So that's kind of a little tricky. But we also know that V equals R omega. Well, how about that? So now that we put that together, we can kind of think about how we do a little bit of substitution. And we end up with an equation. See how this works right here? See how this equation might work by substitution? Yeah.
We also give an acceleration formula for any given.
What's that now?
So in the question it says calculate the acceleration before the jump.
Yes.
Should we also give just a general acceleration like equation based on time?
The time isn't pertinent here because let me see. Yeah, because the acceleration is going to change. So this would be the maximum acceleration which occurs at its amplitude. Now, and I think I understand what you're asking, and let me do a little explanation of what I think you're asking. Okay? Calvin brings up a really compelling idea, I think. And that is, at this positive amplitude right here, we have our maximum negative acceleration going that way. We have our maximum force that's negative going that way as well. And of course, that force is causing the acceleration. We have zero acceleration right here, and we have zero as our force right here. So you know what that means? We have lots of accelerations in between here, zero. And then we have lots of positive accelerations if we were to come on this side. If we're at our negative A, we've got the reverse of this. So the problem is calculate the acceleration of the floor due to this simple harmonic motion as the amplitude of the floor's motion near the motor is 3 mm. Okay? So if you're at the amplitude, you can get an acceleration. So that's why it should say calculate the maximum acceleration of the floor due to simple harmonic motion. That would be a much better wording of this. In fact, I think I'm going to change it right now. Okay? Change it right now. Does that help? That right there. That right there makes a big difference, huh? I'm with you. Okay, we just have to get creative in solving these little problems. And this creativity we're going to get from solving these problems, we just need to keep solving them and solving them and solving them and solving them. So, my wonderful people, let's work on solving problems. All you need is a calculator. My at-home people, go into the week 31 folder, and you all can solve problems with us. If your name is Ashima, you're going to go to the week 31 folder, and you can solve these problems with us as you watch this Castify. Cool? Cool. All right. You look purple. You look purple. I think your favorite color is black because it matches your head. It's really, really dark brown. But I don't know why. I don't know. I think your hair is a little dark. You and Cushy. Cushy's hair might be darker than yours. It just might be. All right. Let me see. Man, that's really close. I think Ashima wins for dark hair. Go red or black, my friend? Everybody got an eraser? Fantastic. So it's quiz day, and we're taking a quiz on simple harmonic motion. We've sat there and we've thought about it, and we know that there's going to be equations that just aren't provided on the AP1 exam. I wish that the AP1 exam had more simple harmonic equations on there. But if we took a brief look at what they're actually going to supply to us, it's not like they're going to leave us completely hanging and offer nothing. In fact, there is a good deal of equations pertaining to simple harmonic motion. Look what they give us. Centripetal acceleration is W squared R, and if R happens to be the amplitude, that is our question we just did. All right? It does have simple harmonic motion due to Hooke's law right here. It does have spring constants. It does give you x max cosine, frequency time plus phi, phase shift, whole thing's called phase. It does say t equals 2 pi over frequency equals 1 over f, angular frequency. That's good. And then it gives us our periodicity of spring and periodicity of the pendulum right through here. That's cool. All right, that's cool. At least we get that. Ladies and gentlemen, RLAs, I hope you opened up the sheet that was in Week 31 folder. I think I'm just going to do it as a PowerPoint. I think I am. Oh, this one's better. Yeah, that's the one we're doing. So, ladies and gentlemen, without any further ado, let's solve this question. Let's solve this question. Okay. Talk to me, Jeremy. Jeremy, what equation do you want to use to solve this?
I want to use the f equals kx.
Yes, sir. Very nice. What answer did you get, my friend?
The answer is 4.2.
There you go. Now, it doesn't seem like Hooke's law is very prominent in the chapter we were doing 15. In fact, we picked up Hooke's law in a chapter a long time ago. But this K value is what dictates the speed of how things move. Okay? So just keep that in mind that oftentimes we've got to do some substitutions to get things figured out. So I don't want you to forget about this. That's the reason why I put it on. Jeremy, that was nice. Good explanation. That was nice. All right. So what if we triple the weight suspended vertically from a coil spring? What will that change in the displacement of the spring? Is it A, B, C, D, or E? Colshaw, what do you think the answer is to number 3?
D.
Well, you're really close. What equation are you going to use?
Probably U equals 1/2 kx squared.
Now, I love the fact that you just have the energy equation memorized. That makes me super happy. So, if I'm painting this picture of a spring that's just sitting here with a mass. So, this mass, obviously, once we put it on the spring, this mass gives us a distance x. It then wants to know, in the next scenario, if we are to go with 3m, we know it's going to stretch by some factor. Now, if this asked for the energy, absolutely correct. The energy increases by a factor of 9. But this is asking actually for displacement itself. And believe it or not, we're going to use the same equation again. So the answer is C. So Cole, in fact, had good knowledge. But this problem is kind of set up as a trap to make you go down that road. Nice job, though. At least you remember that, and that makes me happy. And that's why we're doing this today. We got to do a little bit of myth busting before we can move on and be done. Because we're done with this unit after today. Speaking about an object for which F equals kx, why does that say positive? What will happen if the object is moved away from equilibrium and released?
That's supposed to be a negative.
It is. Whoa. That's just a typo. Oh, that is. Yeah. If you don't have a negative kx, there's no Hooke's law. That's a restoring force, not a shoving force. It's a very interesting question. Why don't you draw a horizontal picture and use it to solve this? Like, I think this is hard to do just like in your head. I'm not saying you couldn't do that. Some of you are capable of drawing a mental image and then being able to manipulate it. You know, everybody varies in that ability. I am not tremendously able to do that. When you see me take tests, I am very visually driven. I draw almost everything. So for me, it's quite simple. I just take 2 seconds and I draw a very rudimentary. I do this all the time for simple harmonic motion. Because for me, simple harmonic motion is not calculus. For me, simple harmonic motion is a physical event where I can take something that looks like this and I can apply it to a circular scenario. That's how my brain has always worked. That's how I was taught to do it. And of course, we know that phase shift is. But phase shift doesn't apply to this problem per se. Per se, this drives the reasons why one of those is correct. If it is, Ben, what do you think? Ben likes to put that it will return to the equilibrium position. What will happen is move away from equilibrium and released, it will return to the equilibrium position. That is a true statement as written, but won't it move farther away with constant velocity? Is there ever constant velocity in simple harmonic motion? It will move further away with constant acceleration. Is there constant acceleration? It will move further away with increasing acceleration. If you're moving away from equilibrium, you've got decreasing acceleration. Odd that is the correct answer. But a lot of people think that's too simple. They move on and they select one of the others. So it's almost like red herrings are thrown in. That's very cool. We're going to skip this. We did this when we did our unit on energy too. So it's okay to think of things in terms of energy for this unit. It's absolutely okay to do this. Look, it's putting like little jagged ends on my smartboard. It's cool. It's like Halloween font up there. And every horror movie, every demon kind of writes like that on a wall somewhere. Okay? Usually they write physics because that seems to scare a lot of people. Gee, you can laugh. It's fine. Sorry, she's too engrossed in what she's doing to be amused by me. Free, what equation are we going to use, homeboy?
What?
What equation are we going to use, in your opinion, to solve this?
Velocity of the V equals A omega cos omega t.
That would be great if we could convert all of those into the omega squared A equation. It's actually easier than that. What type of energy do we have initially? Like, if we were doing bar graphs, what type of energy do we begin with? And then what kind of, go ahead. Yes, sir. It's all spring energy. What's it become?
Becomes kinetic energy. Yeah.
There we go. So, it's saying, what is its speed at the instant its displacement is that? So we're saying, we're not at the amplitude here. Okay? So, if we're not at the amplitude, then that means we're moving a little bit. So we got to kind of rethink how we're going to do this energy bar graph. So I'm going to rethink it this way. I'm going to say that all the initial energy is 1/2 K A squared equals look what I did there. And then, believe it or not, it becomes an equation that I memorized. It's Kim's axe equation. But that's what happens when you isolate for V in this equation. You can just do that. Sorry, this thing is writing really rickety. Anybody have an answer for me? C is it. C's right. Okay. Awesome. Awesome. Look at my bar graph. All of the initial energy I get out of the spring, if the spring isn't all the way back at equilibrium, there's still some energy left in the spring when it's mid-flight. And you know, you almost have to do an energy bar graph to kind of wake your brain back up to that. All right, babies. This is us. This is where we are right now. And I believe that the typing on this is, like, I don't know why those aren't separated. Sorry, I'm making improvements on this. Sorry, I know you all out there in RLAville, this won't remodify your gain dog, but it's okay. We've stared at this equation enough now. We should be able to answer some questions about it. Oh, that's horrible too. No one writes it that way. Boy, the next time I take something from a website, I'm gonna make sure. You know, who are these people? I think this is a little more like what we're used to seeing, correct? They weren't mathematically wrong, they just typed it funny. This is from University of Rochester. There, I gave them credit. Now, Lucia, before we answer this question, what do we call this part of the equation? Yes, ma'am. That is our amplitude, okay? Cosine is cosine, but why is it cosine again? Do you remember? Could you walk me through why it's a cosine and not a sine? Yeah, because it's x and not y. That's it. I mean, it's as simple of thinking in your mind that, geesh, that's the amplitude in this problem, which is x max. And we're actually trying to physically find out what this x position is of that dot as it relates to that dot, for sure. And then, what is this junk in here? Yeah! Angular frequency multiplied by time by a phase shift, if there is one, and guess what? This is a plus 0. Okay, there's no phase shift. So when we graph it, we just graph it without a phase shift. That's all. Okay. Good job. So we've kind of dispelled the myth of how difficult this equation is. It's really not that difficult. But we do have to kind of remember what we're going to do with the omega. So what are we going to do with that omega, Lucia? This is your problem. How does that piece into all this stuff? And how does it piece into periodicity? There it is. So what's our answer, young lady? This is a mathematically it's kind of weird how you have to set this up to get it. We got a substitute. Yes, ma'am. And here's how she did it. Sorry, I wrote it too quick. How about that? She just substituted, because that is that part right there. So then you just do a little algebra, which I know you guys can all do algebra, bruh. That's the number 1, by the way. 32. Nice job. Yeah, this unit is not as mysterious as it appears on the outside. Same problem, just asking for the position at 5 seconds. So now we're saying that this thing was allowed to go around the circle for 5 seconds. Where is x? X here? Is x over here? Is it here? Here? Where? There's lots of possible x's, including equilibrium, right? X could be right at 0. So where is it at 5 seconds? Well, that's going to be dictated by how fast it's spinning around the circle. How fast it's spinning around the circle is that angular frequency. And then the amplitude itself is a constraint. We know the circle itself is only 16 centimeters big. Pretty easy, isn't it? Pretty easy. Shiv, what do you like? A, B, C, D, or E? Put your calculator. You have a calculator. Do you need a calculator? You ever seen a calculator? Seen one. Ladies and gentlemen, let the record state that Shiv has seen a calculator before in his life. Hard to do. I see. I gotta set up. I see the calculator. Easy. Cushy, what do you think it's going to be? Cushy thinks it's D. Okay? That should look familiar to some of you if you've been on Schoology. Now, some like so funny. Some. What'd you do to solve that?
I put 5 in 13. So I got.
That's it. It's literally it. Literally it. And then did you take the cosine of that in radians? Gotta have your calculator in radian mode. When you're doing cosine of this function here, gotta be in radian mode to modify it. Okay, if you're not in radian mode, you're gonna come up with something redonkulousness. Thought question, people, just a thought question. Think of a pendulum like that. A pendulum bob means just a small metal object. We want to know where's the kinetic energy? At max? Is it here? Is it here? This is pretty straightforward. Calvin, what do you think? Zero displacement, you got that. I'm with you. We need an equation based on periodicity to solve this. So we want to triple the mass of the bob on a simple pendulum. Pendulums work on this. If you've got a spring, periodicity of a spring operates on this. So you have two equations for periodicity. Do pendulums usually have springs involved? No, that'd be an awfully weird pendulum, right? They're trying to trick you. This is the period of a pendulum. If that's true, Benny, what do you think? A, B, C, or D, or E? Right on. The size of the mass does not dictate the periodicity of the pendulum. Okay? So there we go. All right. You guys have done fantastic. For my, hey, hit submit and, well, hit turn in Cami, please. And you guys can turn that in. And what I'm going to do is let you guys, I'm done with you guys for today. I'm going to pass out a computer sim that I want done by Saturday. But that's literally, this is literally it. I think what I'll do with this unit is I'm probably going to give a take-home test for it, as opposed to a sit-down test. And then we will begin gravity on Thursday as planned. Okay? So that's where my brain is wandering right now. So hopefully that makes sense. And life is good. So for everybody, we're literally done. You can do homework if you want to. I don't care. You can do nothing if you want to. Just if you put your boards over there and put your stuff away, I feel like that's it. I feel like that's a wrap for today. RLA kids, you can be done as well too. But this is good. You know, hopefully you're going away feeling like I know some of this stuff. It's not quite so scary. Because that's my intention.